Alright, so in the previous class we had this symmetric matrix A, and for that we had found out the eigenvalues as 4 and 2. I have not yet given actual definitions, we will give it afterwards. And then there was this corresponding things that I have here, 1 1 and 1 minus 1. I would like you to understand that I have this matrix A with me, and this was with respect to the standard basis of R2. So, this matrix, when we write a standard ordered basis. So, whenever we write a matrix, generally it is in terms of a standard ordered basis. Now, I want to take my ordered basis B as B of R2 as 1 1 and 1 minus 1. If I take this as my ordered basis, then this matrix I can define my operator T from R2 to R2 by T of x is equal to Ax. And now if I want to look at the matrix of T with respect to this basis B here and B here, then recall that I need to compute T of 1 1, I need to compute T of 1 minus 1, I need to compute these two, and this has to be evaluated with respect to the ordered basis B. So, this is my matrix TBB, fine. So, this is same as T of 1 1, alright, look at T of 1 1, it is A times 1 1, and T of 1 minus 1 is A times 1 minus 1, which is nothing but 4 times 1 1, and so I have to evaluate with respect to B, these have to be evaluated with respect to B, that I will do afterwards, and this is nothing but 2 times 1 minus 1, and this has to be evaluated with respect to B for me. So, when I evaluate with respect to B, what I get here is 4 0, because it is 4 times the first vector and 0 times the second vector, and this is 0 2 because it is 0 times. So, if I look at this part, it is 0 times 1 1 plus 2 times 1 minus 1, and these are the elements of the ordered basis. Fine. So, what we see is that we have got an ordered basis which has come from some calculation, we will understand those calculations, alright, and things have been nice. That is one thing that we understand, that I am able to get matrix A in terms of a diagonal matrix with respect to some ordered basis, alright. That is one thing that we see. Another thing that we need to see here is that look at the trace of the matrix. Trace of the matrix A is 6, which is same as 4 plus 2, alright. And let us look at the determinant of A. Determinant of A is 9 minus 1, which is 8, which is same times 4 times 2, fine. And we also saw that since A is symmetric, alright, we could talk of x transpose Ax being 1. So, we could also talk of all x belonging to R2, x belonging to R2, such that x transpose Ax is 8 or something I wrote, I do not remember it exactly what I wrote. So, this gave me an ellipse, and the minor and major axis of this ellipse came from these two vectors 1 upon 1 and 1 minus 1, alright. So, it gave me the minor axis as one of the axes as x plus y is 0, this gave me one of the axes as x minus y is 0, alright. So, the question is, it is just a chance factor or is there some theory which gives you all these things, fine. So, let us look at another example, example 2. So, this time I take the matrix A as 9 minus 2 minus 2 6. So, as done previously, we would like to compute determinant of A minus lambda I, which is same as 9 minus lambda minus 2 6 minus lambda. So, this is same as 54 minus 15 lambda plus lambda square minus 4, which is same as lambda square minus 15 lambda plus 50. So, equating lambda square minus 15 lambda plus 50 is equal to 0 gives me lambda minus 5 into lambda minus 10 is equal to 0. All right, fine. So this implies 5 and 10 are the numbers that we need to look at, are the numbers for which null space of A minus lambda I is not a non-trivial subspace. Or if you want to say, what we had looked at is that if I want to look at A minus lambda I, this is equal to 0, then this star has a non-trivial solution if and only if lambda is equal to 5, 10. These are the only two choices for which it will have a non-trivial solution star, otherwise it will have a trivial solution. Fine. Here again I want you to note that, look at determinant of A. Determinant of A is 54 minus 4, which is 50, which is same as 5 into 10, and trace of A is equal to 9 plus 6, which is 15, which is same as 5 plus 10. Fine. What about getting an ordered basis? So I hope I have done my calculations correctly. So I would like you to verify that. So verify that if you take B as, so B as 1, 2 and minus 2, 1, if I take this is again a symmetric matrix, you can see here. All right. If I verify that, if I take B as this, then T, the way we define earlier, T of BB will be equal to 10. So it will be 10 here, 0 here, 0 here, 5 here. All right. So this is the way it will look like. Just try that out yourself. And again you can talk in terms of, it will turn out to be an ellipse. So if you want to look at x transpose AX is equal to some number, say 50, x belonging to R2, such that this happens. So then it will be an ellipse with axis. So find out the principal axis. One of them will be x plus 2y is equal to 0, and the other will be y minus 2x is equal to 0. All right. So just look at, depending on these parts that I have got, the ordered basis, the axis comes from there. Is that okay? Fine. So I will not look at the ones which are slightly different in the sense that which are not symmetric, but for symmetric matrices also, non-symmetric matrices also, you can get such things. All right. So let me now go to the theory. We have seen certain ideas, certain things here, and now I want to understand things. Fine. So let's go with definitions and so on. Motivation is enough. So definition. So let A be an n cross n matrix with real entries or complex entries, with real oblique complex entries. I would like you to emphasize one thing here, that all our work or discussion in this chapter, all right, will be over the vector space Cn over C. Fine. So we are not going to look at Rn over R because there will be a lot of problems that will come into play. The theory has to change. So we will look at Cn over C, so that you can say that if I have a polynomial of degree n, I will have exactly n roots. All right. I cannot talk of that when I am looking at real numbers. For real numbers, for example, the polynomial x square plus 1 does not have any root. Fine. It is only complex numbers that comes into play. So therefore we will be looking at only complex numbers, even though our examples, almost all the examples will be real numbers, but we will need Cn over C to do our work. All right. Otherwise you cannot build up the ideas. Fine. So for us we need Cn over C. So, recapitulate yourself and then come back, all right, to understand things. So, definition, so this is the assumption of definition 1, all right. A scalar lambda belonging to C and x belonging to Cn, lambda and non-zero x belonging to Cn, such that Ax is equal to lambda x, the scalar lambda, and this are said to form an eigenpair lambda comma x for the matrix A, all right. So, I am saying eigenpair, fine. So, lambda is called an eigenvalue and x is called an eigenvector, So, it corresponds to something corresponding to lambda, all right. So, you have to set together eigenpair, if when you say, then lambda is an eigenvalue and x is the corresponding eigenvector. Is that okay? So, that is important for me. Further, you need to understand some things which are important, that many books they use the word, in place of eigenvalue they use the word what is called latent value, all right, or they may also use the word characteristic value, and there are other names also. I will not get into those parts, but find out yourself, all right. So, latent root, latent value, characteristic root, characteristic value, and so on. There are so many names that they have, but the idea is simple, that you are looking at the system Ax is equal to lambda x and you want lambda to be a scalar complex number and x to be a non-zero eigenvector. X has to be non-zero, this x non-zero eigenvector is very important. 0 is not allowed, fine. Not only that, now suppose that I have this lambda comma x is an eigenpair. So, if lambda comma x is an eigenpair, then for any c belonging to complex number, c times x is also an eigenvector for lambda, all right. Verify it, a times lambda x, a times Cx is equal to c times Ax, which is c times Ax is nothing but lambda x, which is same as lambda times Cx, all right. So, you can see that you get here Ay is equal to lambda y, where lambda is equal to c times x, fine. So, any multiple of an eigenvector is also an eigenvector, all right. So, what it means is that this implies any non-zero multiple of an eigenvector is also an eigenvector, fine. Further, if I suppose, suppose x1 and x2 are two linearly independent eigenvectors for lambda. Lambda is the same, all right. So, then what we are saying is that a x1 is equal to lambda x1 and a x2 is equal to lambda x2. Then a times cx1 plus dx2 is same as a of cx1 plus a of dx2, which is same as c times ax1 plus d times ax2, which is same as, again lambda will come outside, lambda times cx1 plus lambda times dx2 same as lambda times cx1 plus dx2. So, you can see that a of y is equal to lambda y, where y is cx1 plus dx2 for any c comma d belonging to the complex number. All right, fine. So, what we are saying here is that if I have a eigenvector x, then a non-zero multiple of this is also an eigenvector. I need a non-zero basically because an eigenvector is supposed to be a non-zero vector. All right, that is one thing. If x1 and x2 are two linearly independent eigenvectors, if they are two linearly independent eigenvectors, then their linear combination is also an eigenvector. So, what we are saying is that the set of all eigenvectors corresponding to a fixed eigenvalue lambda forms a subspace of Cn over C. All right, this is important. It forms a vector subspace. Fine. And if you see, basically what we are doing is at each stage we are solving the system Ax is equal to lambda x. So, basically what we are solving is Ax is equal to lambda x for x not equal to 0. All right, fine. So, what we are doing here is we are looking at all x belonging to Cn such that Ax or such that A minus lambda I of x is equal to 0 vector. So, this is called the null space of A minus lambda I. So, fix lambda and consider this. All right. So, all the eigenvectors they come from here. So, eigenvectors are a basis of this space. So, important thing that you need to understand here that when I am looking at eigenvectors, when I want to give you a set of eigenvectors, those eigenvectors must be linearly independent. All right. So, whenever you give a set of eigenvectors is given, a set consisting of eigenvectors is given, that set must be linearly independent. So, if you give a set which you say is linearly dependent, at the same time it is an eigenvector, then the two things do not make sense. All right. That is a statement which is vacuous, which does not make sense. So, linear dependence and eigenvectors, they do not go together. When you are saying that you have given a set which is set of eigenvectors, that set must be linearly independent. Fine, that is very important. So, linear independence is very, very important because you want a basis of this null space of A minus lambda I, you do not want anything else. Fine. So, I have given you the idea of what is called a characteristic vector or an eigenvector, null space, latent root or characteristic root or eigenvalues and so on. Fine. So, let us try to now prove results for these ideas. All right. So, theorem. Fine. Let A belong to Mn of C. So, as I said, most of our examples will be real numbers, but we will be working over complex numbers only. All right. Fine. And lambda belong to C, then the following statements are equivalent. A, determinant of A minus lambda I is 0. B, I wrote the other way around, alpha lambda is an eigenvalue. Eigenvalue of A. Fine. So let's try to prove this. What do I mean by saying this part, that the two are equivalent means whenever this is there, then I am saying it is an eigenvalue, but the idea of eigenvalue and eigenvector had nothing to do with the determinant. So the idea of eigenvalue and eigenvector was that if lambda is an eigenvalue, all right, then we needed a non-zero vector x belonging to Cn such that Ax is equal to lambda x, all right. So if I cannot find, so if we cannot find any x belonging to Cn, x not equal to 0 such that Ax is equal to lambda x, then lambda is not an eigenvalue. All right, this is what you have to be careful about, that the definition clearly says, look at the definition here, that a scalar lambda belonging to C and a non-zero x such that this happens are said to form an eigenpair, and from that eigenpair you get the eigenvalue and corresponding eigenvectors. If you cannot get an x which is non-zero satisfying Ax equal to lambda x, then you do not have an eigenpair. That is very, very important, all right. So that comes with that part. So let us try to prove that A and B are equivalent. So assume that B is true. If B is true means you have Ax equal to lambda x coming into play. So x is a non-zero solution, and therefore A minus lambda I of x is equal to 0 has a non-trivial solution, and whenever we have that A minus lambda I of x has a non-trivial solution, implies that, fine, A minus lambda I is not invertible. So recall the 6 or 7 conditions that I had, and which implies that A minus lambda I is singular. And what does singular mean? Determinant of A minus lambda I is 0. All right. So recall things here very nicely. There were 7 or 8 in the chapter on vector spaces. We had only 6 of them. When we went to determinant, we added that part and things like that. Fine. So linear system of equations and invertibility and so on, you all have these things. All right. So this was defined only at the end of chapter 2, which was about linear system of equations. All right. All these conditions were given to you. So if lambda is an eigenvalue of A, implies that Ax equal to lambda x has a solution for some choice of x which is non-zero. Since x is non-zero, so it has infinite number of solutions. All right. So this has an infinite number of solutions. Once you have infinite number of solutions, so the matrix must be non-invertible, it should not be invertible, and therefore it is singular because they are all equivalent conditions, and therefore you get determinant of A minus lambda is 0. Now A implies B. Suppose determinant of A minus lambda is 0, this will imply that A minus lambda is singular. That will imply that A minus lambda I is not invertible, and therefore the system will have infinite number of solutions. All right. Since it has infinite number of solution, I can choose one which is non-zero and get my answer. Fine. So they are all equivalent. There is nothing special about it. Fine. Now some more definitions. What are called characteristic values and things like that. So let A belong to Mn of C. I may not write again and again this part, A belonging to Mn of C. We will just assume it is. Then 1, determinant of A minus lambda I, or in many books they look at determinant of lambda I minus A. So A is n cross n, so I is also, it is I sub n that you have. Fine. Now what is determinant here? This is a polynomial in lambda of degree n. Is that okay? And this polynomial is called the characteristic polynomial. All right. So this is the reason. So what we are saying is a compute determinant of lambda I minus a. It is a polynomial in lambda of degree n, and this polynomial is called characteristic polynomial. So the roots of this polynomial are called characteristic roots. Fine. 1, 2. So the eigenvalues or characteristic roots or values, all right, or latent roots are the roots of the characteristic polynomial. Fine. So if I write this, if I donate this polynomial as P, so books have different notations, so I don't know what I've used. P of A, no, it should be P of lambda A. P lambda of A or just P lambda. Fine. Then we are saying that just compute P lambda, put it to 0 and get the roots. Fine. Third, look at all this set lambda belonging to C such that P lambda is 0. All right. So this set is called the spectrum of A, or which is same thing as saying that the collection of eigenvalues of A. Is that okay? So in the first example, if you recall, fine. So in the first example we had this notion of, let me give one more definition. Look at the set mod lambda such that lambda belongs to C. So this is a collection of numbers. I want to look at the maximum of this. So this maximum, all right, this is called the spectral radius of A. All right. So they have different definitions that you have here. So example, let's go back to example. The first example that we had was, I took A as I think 3 1 1 3. So for this matrix, P lambda was equal to x square minus 6x, yeah, plus 8. Fine. Another example, I took A as, I don't remember it, so let me go back and see what I had taken. It was 9 minus 2 minus 2 6, and for this P lambda was x square minus 10x plus 50. Fine. So look at this, the roots of this were 2 and 4. Fine. So therefore a spectrum here is 2 comma 4. We write it as a set, and we write generally as sigma of A, sigma for a spectrum here. Is that okay? In this case, we had 5 and 10 as our roots. So 5 and 10 are the things. A spectrum was, so a spectrum which is sigma of A is 5 comma 10. Is that okay? A spectral radius here is 4, and here the spectral radius is 10. All right. So that's for now. We'll look at some things more in the next class. Thank you.